Like there can be society within a society and a family within a family. We can have groups within a group, and these are called subgroups. In this video we will see subgroups. Subgroups. Subgroup. If a subset H of a group G is a group under the operation of G, we say H a subgroup of group G, and we have some notations for this. Notations. H, this is a notation for subgroup. We say H a subgroup of G, and if this is strictly, then we say it's a proper subgroup of group G. Let this be our happy little group G, and under some operation star it forms a group, and within this set G we have another set. Suppose this is the set H, and this set H under the operation star forms a group. That means it will satisfy all four group axioms. If that is the case, we say H is a subgroup of the group G. And let us see some of the examples. We have first one. We have first seen this set of real numbers under operation of addition is a group. And also we know the set of integers is a subset of the set of real numbers, and this set with addition also forms a group. So we can say that the set of integers is a subgroup of this group G, of group G. Second, see, we have also seen the set of non-zero complex numbers under multiplication is a group, and this set we have already seen it, 1 minus 1 I minus I, in the video of binary operation. We have seen this is a group, and in that video we have seen this forms a group under the operation of complex multiplication, and this is a subset of non-zero complex numbers, and we can say this is a subgroup of our group G. This is the group G. Please pause the video to note. I will erase. We have also seen, let us see another example. We have also seen GLNR. This is general linear group. This is a set of matrices with real entries, and matrices are square matrices of order n, and operation here is matrix multiplication. Also the matrices have non-zero determinant, they are non-singular, they are invertible matrices. This will form a group under the matrix multiplication, and this is another group. This is also a group under the matrix multiplication, and here we have the set of all matrices, square matrices of order n with real entries whose determinant is 1, and this is obviously a subset of this set, and this forms a group. We have also seen this, so we can say SLNR not only a subset of this set, it is a subgroup. To show something is a subgroup, since it is a group, we have to show all 4 group axioms, but we have some subgroup tests, and those tests says you don't have to show all 4 group axioms. You can show something is a subgroup if it satisfies some of the properties, and we will see subgroup tests. Let me erase this. First we will see 2-step subgroup test. We have 2-step subgroup test. This subset is not only a subset of a ordinary set, it is a subset of a group. So it actually inherits some property of the group. Therefore, it is not necessary to show all 4 group axioms, and by this subgroup test we will see our work will be reduced. And first one is 2-step subgroup test. As the name says, we have 2 steps. So if G be a group, H be a non-empty, it is important, non-empty subset of G, and if, as the name suggests, we have 2 steps. First step, for any 2 elements of the subset H, its product also belongs to the subset H. First one is, for every pair of elements of the subset H, we must have its product also belongs to the subset H. Second, for every element of the subset H, its inverse also belongs to the subset H. We have used multiplicative notation, and so we have not mentioned star. AB, this means A is operated with the operation of group G with the element B, and A to the power -1 is the inverse of element A, and if this 2 steps is satisfied by the subset H, then we can say the subset H is a subgroup of the group G, and we will prove this. In proving, we will show if H has only these 2 properties, then H will satisfy all 4 group axioms. First one is closure. closure, it is given that by the first step we have already closure, isn't it? For any two elements of the subset H, its product also lies in the subset H. And this is the property for closure. It is given that for all AB in the subset H, we have its product also belongs to the subset H. Second, also associativity, and this property will be inherited by the subset H from the group G, because for any three elements of the subset H, these three elements also belongs to our group G, because H is a subset of G and every element of H lies in the subset, lies in the group G. And we have and this is the property for associativity. For any three elements of the group G, we have this property. So take any three elements of the set H, they will also satisfy this property, because the property is inherited from G to H. Third one, some of the axioms or some of the properties are for existence and some of the properties are for are rules, like commutativity, associativity. These are rules. Existence of identity. Identity should be in the group. Existence of inverse. Inverse must be in the group. So these are existence. If A is in the group, its inverse must exist in the group. And the closure property. If two elements are in the group, their product also belongs to the group. So AB must exist in the group. So these are existence. And commutativity, associativity, these are rules. Like in commutativity, we have AB and we have BA. We are just checking if they are same or not. If that is the case, then commutativity. Or associativity, this is same as this one. So to showing something, some two elements are same, we must have those elements prior to that. So we have already these two elements and we are showing if they are equal or not. So this is a rule. Show them if these two are equal or not. So some of the axioms are for rules, some of the axioms are rules, and some of the axioms are existence. And associativity is a rule. If a rule is for a bigger set, then that rule will satisfy for some for a smaller subset of that set. So for any three elements, if this is the case in the group G, and H is a subset of G, so take any three elements of the subset H, they will also satisfy the rule. Like if there is a rule for all students of a college, then a small department will also follow that rule. That is the case here. Associativity is inherited from the group G to H. Now we have identity. See, we have only two properties of H. The statement is saying H has these two properties. If these two properties are enough for H to have all group axioms, and closure is by the property of H, associativity is inherited, identity is not mentioned here. We have to deduce identity from these two properties. See, we have, this term is important. We have the subset H is non-empty. So what happens if something is non-empty? If something is non-empty, there must exist some element in that set. So there exists, thus there must exist an element A in the subset H. And if A is in the subset H, by the second property of H, we have A inverse also belongs to the subset H by the property of H. A and A inverse belongs to the subset H, and first one is saying if two elements are in the set H, its product is also in the set H. So the product also belongs to. That implies E is the identity, belongs to H, where E is the identity. A and this is inverse of A. If they will be combined, it will give the identity. And the last one we have the inverse of every element, and it is given that for all A belongs to the subset H, we have its inverse also belongs to subset H. The inverse condition and closure condition is already given, and associativity is inherited, and by using these two steps we can show the identity is also in this subset H. Therefore H is a group under the operation of G, operation of group G, hence a subgroup of G. Please pause the video to note. I will erase. So two-step subgroup test says if a subset H has these two properties, then it will be a subgroup of the group G. It will satisfy all group axioms under the operation of group G. Example. In this example, we will have a group and a subset of that group, and we will show that that subset forms a subgroup by using two-step subgroup test under multiplication. We have seen this is a group, and I am taking our subset H with the set of all elements in the form 2 to the power alpha, for alpha belongs to the set of integers. So we have to be clear what our subset is. The subset H contains all those elements in the form of 2 to the power alpha. Alpha is an integer. If alpha is 0, 2 to the power 0 is 1. If alpha is 1, we have 2. Alpha 2, we have 4 and 8, 16, so on. And if alphas are negative, for negative 1 we have 1 by 1 over 2, 1 over 4, for negative 2, 1 over 8, and so on. This is our subset, and clearly all these are real numbers and these are non-zero real numbers. 0 can't be written in the form of 2 to the power alpha. So this is our subset H. We are going to show H is a subgroup of the group G. So it will satisfy all 4 axioms of the group, but we will not show all 4 group axioms. We will use the 2 steps of group test. It is saying you have to only show these 2 properties. So first we will show the closure. This one is closure, and we will show the closure. Let us take 2 elements from the set H. Let A and B be 2 elements of our subset H, and if A and B are in the subset H, then A must be in the form of 2 to the power alpha, and B also must be in the form of 2 to the power alpha for some integer alpha. Thus A equals to 2 to the power, suppose it m, and B equals to 2 to the power n for some mn integers. And now we will show their product also belongs to the subset H. The product AB equals to 2 to the power m times 2 to the power n, or I can write this way, which is same as 2 to the power m plus n. We have to show AB also belongs to the subset H. Something to be in the subset H, it must be some power of 2, and that power must be an integer. We already have m and n are integers. Since m and n are integers, its addition is also an integer. Let us write that. Since m, n are integers, we have its addition, m plus n is also an integer. Therefore 2 to the power m plus n belongs to the subset H, and which is nothing but AB. So from the 2 steps we have proved the first step. So H satisfies the first step. H is closed under the operation of group G. Pause the video to note. I will erase. The next we have to show for every element in the subset H, we have its inverse also in the subset H. Let me erase. Second one, let take any arbitrary element in the subset H, and if A is in the subset H, A must be some power of 2. A equals to 2 to the power m for some m in the set of integers, and we will show that its inverse also belongs to the subset H. What is the inverse of A? The inverse of A is this one. Why? Because since times its inverse equals to 1, and 1 is the identity, and 1 is the identity of our group G. A inverse is this one, and this is same as 2 to the power minus m. We have to show this one also belongs to the subset H, and we have m is an integer. Since m belongs to the set of integers, its negative also belongs to the set of integers. If 1 belongs to the set of integer, its negative. Minus 1 is also an integer. If m is an integer, its negative minus n is also an integer. That implies 2 to the power minus m is also 2 to the power minus 1 belongs to the subset H. That implies A inverse is in our subset H. And we have shown that H satisfies these two properties. H is closed under the multiplication operation, and H has inverse of every element. And by two-step subgroup test, by two-step subgroup test, we have H, a subgroup of group G. Pause the video to note. Now let me erase. Let us have another example, and this example is little bit different. Suppose we have first an abelian group, G an abelian group. So it is satisfy all four group actions, and it has commutativity property also. Let the first and we have two subgroups. H be a subgroup of group G and K be a subgroup of group G. We have an abelian group and two subgroups of the group G. We have another subset HK which is defined as the product of small h small k, where small h belongs to the subgroup H and small k belongs to the subgroup K. This is our subset. Is HK a subgroup of our parent group G? And we will use the subgroup test, the two-step subgroup test. Two-step subgroup test. To apply two-step subgroup test, our subset must be non-empty first. In the previous example, I have missed it. We have to show H is non-empty first, and we already know H has 2, 4, 1, so H is non-empty. First we have to show HK is non-empty. We have, here we will show H is non-empty. H is non-empty. We have the identity, it is the identity of G belongs to the subset H, and E also belongs to the subset K. What is the property of HK? Our subset has all those products small h small k, where small h belongs to the subgroup capital H and small k belongs to the subgroup capital K. So the product E also belongs to the subset HK, because E is an element of capital H and this also element of capital K. That implies E also an element of HK, hence it is non-empty. Our subset is non-empty. Next we have to show two steps. First one is closure. We have to show the closure. For closure, let us take two elements of the set HK. Let small a and small b belongs to our subset capital HK, and by the property of capital HK, if A is in the subset HK and B is also in the subset HK, A must be in this form. A must be some product of small h and small k, where first one is from the subgroup H and second one is from subgroup K. That implies A equals to sum H1 K1 and B equals to sum H2 K2, where H1 H2 belongs to the subgroup H and K1 K2 belongs to the subgroup. This is the property of HK. If two elements are in the subset HK, A must be in this form and B must be in this form, where these two elements are from subgroup H and K1 K2 are from subgroup K. What we have to show, its product lies in the subset HK. The product, now we have AB. We are using multiplicative notation throughout this example. AB equals to H1 K1 H2 K2. This is my first element, this is my second element. And by using associativity, see, associativity says parentheses are redundant. Associativity says we can apply parentheses in anywhere. Parentheses are redundant. Parentheses are redundant and we'll also use commutativity. Commutativity says we can interchange two elements. Interchange. So by using associativity, you can write, this is by associativity. And by commutativity, I can write this one as, therefore it is given an abelian group. If G is not an abelian group, then we can't interchange the H2 and K1 as G an abelian group. Abelian group, it has commutativity. So again, by using associativity, I can write H1 H2 and K1 K2 by using associativity. See, we have H1 H2, two elements of the subgroup H. H is a subgroup, so it is a group under the operation of group G. Therefore, if H1 H2 are subgroup, H1 H2 belongs to this subgroup H, then its product also belongs to the subgroup H, because by the closure property of subgroup H, we have H1 H2 belongs to this subgroup. Also, we have K1 K2 belongs to the subgroup K. Here also we are using the given condition. If H and K are any subsets of the subgroup G, then it may not work. So it is given that H is a subgroup and K is a subgroup. That conditions are also we are using them. That implies K1 K2 also belongs to the subgroup K, and we have this element H1 H2 and K1 K2 belongs to HK, which is nothing but AB. So we have proved the closure property. Pause the video to note. I will erase. Next we have inverse. In two steps of group test. Second step is to show the if any element in that subset, then its inverse also belongs to that subset. Let us take, let A be an arbitrary element of the subset Hk. That implies A equals to some product of Hk where H belongs to capital H and small k belongs to the subgroup capital K. We have to show its inverse also belongs to, we have to show, let us write what we have to show. We have to show A inverse also belongs to Hk. That implies we have to show its inverse belongs to the capital Hk. And it is nothing but K inverse H inverse. By the Subgroups property, we already have, note, H an element of subgroup H, K an element of subgroup K, and since these are subgroups, H inverse belongs to the subgroup H, K inverse, small k inverse also belongs to the subgroup K, since capital H and capital K are subgroups, and by the property of subset Hk, we have H inverse K inverse belongs to the subset Hk. And since G is an abelian, we have as G an abelian group. And this is same as this one. Since G is abelian, it has commutativity property, so H inverse K inverse is same as K inverse H inverse. If this one is in the set capital Hk, this one also lies in the set capital Hk. Therefore we are done. We have proved that this set is a subgroup of our group G. Hence it is proved and we are happy. Pause the video to note. In the next class we will see one step subgroup test, and you can ask your doubt in the comment section and let me know them.